Alrighty. Oh, I also sent out a remind, so this is for people on the video too. I want to make sure this is heard, right? Please make sure you're bringing in that registration information for the AP test, right? Okay, Friday is the due date. Friday is the due date, okay? So, I sent out a class-wide announcement because some of you aren't on, well, some of you aren't on their mind, so I'm saying it right now, okay? Please make sure you're bringing your registration in by Friday, okay? That's tomorrow, right? And then, yeah, and I'll come around and talk to some of you guys hopefully by the end of class, before the end of class, just to check on, make sure everything's okay with that and stuff. So, anywho, let's get into what we're going to do today. So in your notes, we're going to be starting on comparisons of series. Okay, so we're going to add even more to our list of tests that we can use to help determine convergence or divergence of a series. All right. So, for all the convergence tests that we have used so far, okay, the series have been very simple, or at least we've been able to fit them into kind of like a form, right? Okay, and so we've been able to fit them into an exact kind of form to apply a test, right? Any sort of like small deviation that we couldn't, kind of account for, then made a test inapplicable, right? We just couldn't use it. Now, we didn't really see that happen very often because you can't really do much with the test that doesn't work, right? I mean, we didn't really see a whole lot of examples where it's like we can't do anything, right? Because otherwise, well, we wouldn't be able to do anything. It's not good practice, I guess. But anyway, so in a sense, right, these tests have a kind of a similar feel then to those integration rules because again, in integration, we had to match very particular forms in order to integrate certain functions and stuff like that. Okay, so if we look here, right, we see some examples of some series that we can do and some series that we can't do. All right, so for example, the very first one here, letter A, 1 over 2 to the n like that. Okay, what kind of series would we identify that as? It is geometric. Okay, but if you add an n into the numerator like this, is it geometric now? No. So, okay, it is not geometric anymore, right? Okay. So, in other words, this one, we can do this one, can't do this one. Just adding that little n into the numerator there changes what we cannot do. All right, how about letter B? What about the sum from 1 to infinity of 1 over n cubed? We could use what for that? P series. Okay, P series test. All right. But then here, when we have 1 over n cubed plus 1, that's not P series anymore. Okay. In fact, we can't really do that one. Okay. Integral test wouldn't work there either because we can't integrate 1 over n cubed plus 1. All right. So it would be kind of stuck. And then what about right here for letter C? What kind of test could we use here to determine this series convergence or divergence? It is an integral. Yeah, we could let u be n squared plus 1. Du would be 2n dn, so we can take care of it there. So yeah, this is an integral test. We would, of course, want to make sure that, of course, is it, decreasing? Yes, because as n increases, n squared plus 1 kind of quantity squared, that's going to be, your denominator, so it's going to be increasing too. Okay? And it's going to always be positive, of course, and of course, it'll be continuous as well. So integral test would apply here. But here, not integral test, right? Because we just can't integrate that thing now. Okay? Or we could also say maybe it's not integral test because the numerator and denominator there, it may not be decreasing anymore. So maybe we could integrate it. I'd have to think about that. But we can't necessarily use integral test because this thing is maybe not decreasing, right? Maybe it's not decreasing kind of thing. But no, it would be decreasing. Never mind. The denominator is going to go, yeah, big hit big. But anyway, we can't apply the integral test there. Can't integrate that. Okay. So we run into some troubles here, but it's like, man, this thing is awfully close to this, or man, this thing is awfully close to this, or this is awfully close to this. Can we maybe do better, right? Can we do better? And so in this section, we're going to learn 2 additional tests for positive term series. So again, focusing on positive term, okay? These 2 tests will allow us to determine the convergence or divergence of a whole new set of series, okay? And we're going to do that through comparison. we will compare a more complicated series with a simpler series to determine convergence or divergence. Okay, now, Mr. Goff has people actually get into like a very large cardboard box for this demonstration, but I wasn't quite prepared to do that, so instead we're going to just draw a little picture here. Okay, I know, I'm sorry. I know, yeah. I don't know. Sounded like Mike, though. Okay. So I'm going to draw a little box. Well, actually, it's not. Shouldn't be so little, but anyway, you get the idea. Okay. My apologies to all of you artists out there for my not great. Say that's like the open lid there kind of thing. And like this is like there's that. Yeah, no, there's like a lid right there, or something like that. We just can't quite see it. Okay. Happy little trees and stuff like that too. Okay, and we'll say this box. Okay, this box. We'll say it represents a finite volume. Right? The box is not infinitely large or infinitely. It's not infinite of anything. Right? It's finite. The box contains a certain quantity, a certain volume. Okay, and we'll say that if we fit in the box, right? So this could kind of represent then, this finite volume represents then a sequence that would converge, right? Because a convergent sequence, left like a little splotch. Okay. A sequence that converges, right, represents a finite quantity, okay? So we're saying that this is like representing our sequence a sub n converges, okay? And then let's say we have 3 people. So actually what if Mr. Goff selects 3 people. So we'll pick a little person. We'll call them A. Okay. We'll I was going to say Mr. Widmeyer, letter A. All right, letter B, that's a medium-sized person. Okay. And then letter C, a large person. If you want to hit him later or something like that, Madison, you can do that. That's fine. I don't blame you. Okay. So anyway, these 3 people, okay, are going to try and get inside the box. Okay, these 3 people are going to try and get inside the box. Let's say that we send person B into the box, and person B worked. Person B fits in the box. Can we say anything else about the other 2 people and whether they will fit into the box or not? A will definitely fit in the box. Why?
Because he's small.
Because A is smaller. That's right. Okay. So if we get B to work, we know that A will also fit. What about C?
No, definitely not fit in the box.
Better point. We don't know, right? We don't know. Maybe they'll fit. Maybe they won't, right? Oh, is that right? Okay, well. But we don't know for sure, okay? So starting with the fact that B works, we end with these 2 results. Without having to even send A in or send C into the box, we know if B fits in the box, A will, C may or may not, right? Okay. So then what if we send B into the box, right, to get inside the box there? And what if B, we start out with, it does not work? Now what can we conclude? C will definitely not work, right? Because if B is not going to work, then the larger person, C, will also not work. But what about A? What can we say about A? Possibly not, right? We don't know. Is A small enough to still get in the box? Is A, or still going to be too large so it won't fit in the box? Okay. This is the essence of the direct comparison test, which we're going to look at first, and then we'll also talk about a development of the direct comparison test called the limit comparison test. Okay? So what we just did here was kind of like what would be called a direct comparison. So here are our series, okay, the direct comparison test. So in this scenario, we have 0, which is less than or equal to A sub n, which is less than or equal to B sub n. Okay, which is, we should really say, for all n, okay? So every term in A, if you pick like the 5th term or the 100th term or the 1,000,000th term, okay, that will be less than the corresponding 5th term, 100th term, or 1,000,000th term in B, okay? So A sub n, no matter what n is, right, or where you are for your nth term, whatever nth term you're talking about here, that nth term for A will be always smaller than or equal to the nth term for B, okay? So in other words, A kind of represents like our B in this case, right? It's like between 0 and 0 and B. So A is kind of like between, okay, the thing between here. So if we know that B, which is bigger than A, converges, what can we say about A? A sub n will have to also converge. That's right. Okay, because of that. Whoops, I forgot to put the A sub n there. Or I'll rewrite it. A sub n converges to. Okay. Will A sub n converge to the same thing that B sub n converges to? Not necessarily. Not necessarily. We don't know. We don't know. Okay, not necessarily. It doesn't have to. Might not. Okay. Let's continue with that line of thinking, though. If B sub n diverges, what can we say about A sub n? This is inconclusive, right? Because A sub n, okay, sorry, because B sub n is greater than that A sub n, right? If B sub n diverges, well, it's already bigger than A sub n, so we can't really say. So in other words, this is, yeah, the sum from n equals 1 to infinity of A sub n is inconclusive, okay? And we would then try a different test or something like that, right? All right, let's keep going here then, right? So if the sum from 1 to infinity of A sub n, if A sub n diverges, what can we say then? B sub n will also diverge. Okay? That's like, this is like the middle person not fitting in the box, right? A sub n doesn't fit in the box, and so therefore the larger person, right, B sub n in this case, will also diverge. Okay? But then if our middle person, okay, if they fit in the box, what can we say about, B sub n converging here? Well, sorry, let me see here. What am I saying? No. If B sub n, then C sub n, the larger person. It's going to be inconclusive, yes, sorry. So again, A sub n, if it converges, we don't know if C sub n will also fit, or the bigger person there will fit as well, okay? Because that larger series is larger, right? So it's inconclusive. Okay, so that's the idea there. All right, so let's get into some actual problems then. Okay. So, letter A, all right, we're going to, directions here, determine the convergence or divergence of the following series. So, of course, then with this comparison, this direct comparison test, it's up to us to kind of figure out or think up of a series that will, kind of always be less than or greater than, the given one here. And so that way we can then hopefully determine that comparison series, whether it diverges or converges or not, right? Okay? So, this right here, okay, it's very close to, but not quite, what kind of series? A geometric, okay? So this is not a geometric series. Okay? But very close to the sum from n equals 0 to infinity of what? So what geometric series would this be really close to? 1 over 3 to the n, right? Okay. So we will compare the two. Okay. So let's compare them. They're very close to each other, right? Let's compare them. See if we can make up some sort of understanding here. So let's look at our comparison. Okay. Our contender here and see what happens. So I'm going to rewrite 1 over 3 to the n as 1/3 to the n. Okay, right? Because that's more helpful there. Okay. By geometric series test, what do we know is true about this series? Is it going to converge or diverge? Converge because r is less than 1, okay? Absolute value of r equal to 1/3 is less than 1. Okay? So, right, knowing that this converges, if the sum from n equals 0 to infinity of our original 1 over 2 plus 3 to the n, if that's always less than or equal to the sum from n equals 0 to infinity of 1 over 3 to the n, right? So if our original series here, if we can show that it is always less than or equal to our comparison series there, then we will know what about our original series? It must also converge, right? If we can show that our original series is always less than or equal to a series that we know converges, then this thing must also converge. Okay, right? We already showed this converges. If we can just show that this is always less than or equal to this, we know it will converge as well. Okay, and I'll say that too. Then n equals 0 of 1 over 2 plus 3 to the n will converge to. Okay? And so how can we kind of show this? How can we kind of convince ourselves? You might be able to look at it and see, Mr. Wade, this, I'm pretty sure that this thing will always be less than that 1 over 3 to the n, okay? Just conceptually here, I'll just kind of try and explain it, right? They both have a numerator of 1, so that part will always be the same. It's the denominator that's going to be different. The denominator here is 2 plus 3 to the n, so this denominator will always be greater than this denominator. And if your denominator is greater, what does that mean about the overall value of the fraction? It's going to be smaller because you're dividing by a greater number, right? So this is going to be less than this in every case. But, or for n equal to for n equals 0 and beyond kind of thing. But let's just check, and we can do that by just setting up the inequality here. I'm going to run out of space, but I'll do it here. So we'll write 1 over 2 plus 3 to the n less than or equal to 1 over 3 to the n, and let's just see if we arrive at something we know to be true. Okay. Well, we can cross multiply here, 3 to the n over here, 2 plus 3 to the n over here. Okay. We have 3 to the n's on both sides. Let's subtract those. We end up with 0 is less than or equal to 2. Is 0 less than or equal to 2? Always. It's true. Okay, and so we know sum of n equals 0 to infinity of 1 over 2 plus 3 to the n converges. Okay. Now, granted, we're not going to go through this all this writing for all these problems here, but I just want to do it for the first one here, just kind of give you, the idea. Okay, questions on any of that? The biggest challenge here is coming up with the sequence to compare it to, right? Sequence with which we compare it, but it's, well, you'll see here. All right, so let's press on here. Try a different one then. All right. So the next one, letter B. Okay, if you look at letter B there, all right. Considering letter B, right, we can't evaluate this one using any of our prior tests, previous tests, but it's awfully close to what kind of series here? P series, exactly right. Okay, so again, looks like a P series. Okay, and so we will compare to, I'm just going to use some arrows here. We're going to compare it to, and what do you think we should compare it to here? 1 over square root of k, or 1 over k to the 1/2, if you'll just permit me, bless you, to write that out. You're welcome. Okay, now, this P-series test, okay, up to our comparison here, if we apply the P-series test, what do we know about this series? Yeah, it's going to diverge because P is less than or equal to 1 there. Oops, I used k's. Sorry, we're using k's here. From k equals 1 to infinity, again, of 1 over k to the 1/2 diverges by P-series test. P equal to 1/2 is less than or equal to 1, right? Now And again, be careful with that P series and geometric series, right? For a geometric series, okay, right, it's when R is less than 1, the series converges. For P series, it's if P is less than or equal to 1, the series diverges, okay? So it's a little bit tricky to keep those things straight. Make sure you do, okay? So if we know that this diverges, and if we want to get a conclusion for this, what do we want to show that this is? Right. If this diverges, if we want to get a conclusion, if we want to be able to conclude something, if this diverges, we need to show that this is greater than this thing right here. So let's take a look here. So we want to show that 1 over 4 plus, square root of k is greater than or equal to 1 over k to the 1/2. Okay, again, we'll multiply both sides. I'll multiply k to the 1/2 over here, multiply the 4 plus root k over here, kind of cross multiply. You want to think of it that way. Okay. Both sides have k to the 1/2. We'll subtract k to the 1/2 from both sides. We get 0 is greater than or equal to 4. That's false. Okay. So, in other words, the sum from k equals 1 to infinity of 1 over 4 plus the square root of k, okay, is less than or equal to, right, the sum from k equals 1 to infinity of 1 over k to the 1/2, okay? It's this divergent series is greater than this unknown series. So what can we conclude? Inconclusive. Yeah, nothing, okay? Nothing. We'll come back to that one in just a little bit. But for right now, we'll settle with inconclusive. Okay, questions on that one? Okay, so again, you can see there's some difficulty in coming up with these comparisons, right? Sometimes the comparison you want, and you might be able to come up with a different thing to compare it to. You might be able to come up with a different thing to compare it to that you can then show what you want, kind of deal. So yeah, Mike. Yeah. But for right now, we're kind of stuck with that. All right, can I move on here? All right, so let's look at letter C. I'll kind of have to okay. So what might we try to compare this to? What can we maybe rewrite this as? Integral test? Possibly. We do have the ln k, but then we have that k to the 4th there. I'm going to say P series here. Okay, we're actually going to try and use a P series again. Okay, so again, compare to a P series. I'm writing it down for the notes kind of thing. I'm just doing it for the notes' sake. Okay, so a little bit tricky here about how we want to compare our P series. Okay, so one thing I want to say here, okay, is that ln of k, okay, natural log of k is always less than k. Okay, natural log of k will always be less than k. Okay, natural log of k will always be less than k. Okay, with the way the numbers work out here, okay? No matter what you plug in, okay, the natural log of k will always be less than what k actually is, kind of thing. Okay? So, we can compare to the sum from k equals 2 to infinity of k over k to the 4th plus 1. Okay? So instead of ln k in the numerator, we'll put a k in the numerator there to compare it that way. Okay? So right, then we can even take out the plus 1. We can compare it even further here and say, then compare that of 1 over k to the 3rd then. Because k over k to the 4th, what's implied is just a 1 over k to the 3rd there. Okay, so again, we can even leave off that plus 1 for right now. Okay. So, now, what do we know about 1 over k to the 3rd? converges by P-series test. Okay? And then all we need to show, I don't really need to show that 1 over k cubed is related to this, right? I need to show that 1 over k cubed is related back to the original here. Okay? So we're going to relate that 1 over k cubed and that natural log k over k to the 4th plus 1. Okay? How do we want these two things to relate in order to get a conclusion here? If we know that this converges, what do we want to be true about this? It should be less than or equal to the thing that converges, right? So less than or equal to. Okay, so we're going to set it up that way. Hopefully we arrive at a result that will, confirm those things. Okay, so again, I'm going to cross multiply here. We'll have k cubed times the natural log of k, and that'll be less than or equal to k to the 4th plus 1. Okay. Now, multiplying k cubed and the natural log of k is a little bit weird. We're like, what's that going to equal? And how can we compare that to k to the 4th plus 1? But remember, we established kind of up here, we said up here, right, that the natural log of k is always going to be less than k. Okay? And so we're taking something like natural log of k, which we'll say is like less than k, and we're going to multiply it to k cubed. And so the result is going to be something that's less than k to the 4th. Okay, I know I'm writing a little bit of funky math there, right? Putting two less than symbol in there. But the idea is we're taking something smaller than k, multiplying it by k cubed, and so we'll end up with something that's smaller than k to the 4th. And we're saying that's going to be less than or equal to k to the 4th plus 1. Well, is that going to be true? Yes, right? This is something smaller than k to the 4th. This is k to the 4th, and then plus 1. And so, yeah, this is true. And so we can say then, so the sum from k equals 2 to infinity of the natural log of k over k to the 4th plus 1 will also converge. Okay? Now again, I can remember learning direct comparison when I can remember being in your seat learning direct comparison. Okay, because it was so traumatic. Not traumatic, but I just remember like looking at it and be like, how am I supposed to figure out what these comparisons are? How am I supposed to pick it right? How am I supposed to know, like, Mr. Wood, how am I supposed to know that natural log of k is less than k and we're just going to do this mathemagic over here and make it work kind of thing, all right? So I understand. Okay, we're going to learn we're going to learn something that kind of arises from this, and then that'll be more concrete for you there. Yeah?
So since the natural log of k is less than k, you just turned it into k?
Exactly, by comparison. Again, the idea is, we're creating something right here. We then create something a little bit greater, right? K over k to the 4th plus 1 is always going to be a little bit greater than natural log k. And then we create something even a little bit greater than that, 1 over k cubed. Okay? Because that plus 1 there is going to indicate that this is always a little bit smaller than this. And so if we can show that this thing converges, then this and then this will also converge. All right, that's kind of the idea. So, yes. So it is a little mathemagic. All right, in a sense. All right. Anyway, last one here. Okay. So again, what kind of series test might we want to try to use here? Another P series, exactly right. Okay. And so for this one, we're going to be comparing it to I'll write the sum here. The sum n equals 1 to infinity of I'll leave the numerator the same, and then what should be in my denominator? What am I going to compare it to in the denominator? N to the 3 halves. Exactly right. So again, we're going to drop that plus 2 piece. We're just going to keep the cube and then the square root, of course, too. So it's n to the 3 halves. Okay. Now, what do we know about this P series right here? It will what? It will what? Right, so P series test, right? Okay, remember back up here we said it diverged for P equal to 1/2, which is less than or equal to 1. Okay, so for greater than 1, P series test converges. P equal to 3 halves is greater than 1. Okay. So then, if this thing converges, how do we want it to relate to this? We want this series to be greater than the original one here. So let's set it up. 3 over the square root of n cubed plus 2. We want it to be less than or equal to the 3 over the n to the 3 halves. Again, cross multiply. Square root of n cubed plus 2. Okay. To continue, we can divide both sides by 3, so we end up with n to the 3 halves is less than or equal to the square root of n cubed plus 2. How can we proceed from here? Well, we could square both sides, for example, right? We'll end up with n cubed is less than or equal to n cubed plus 2. And at this point, we can kind of say, is this true?
Yes.
Right? Yeah. We're going to take n cubed, we're going to add 2. That'll always be greater than or equal to n cubed. Again, this is for, of course, these are for n values that are greater than or equal to 1, right? This wouldn't hold if we had negative n values necessarily. Okay. Oh, wait, never mind. It would still, never mind. Yeah, so anyway, it does still hold. But anyway, my point is, this is true. And so therefore, if this is always going to be greater than this, if this converges, this must also converge. Okay, our original series will converge because the comparison that's always greater also converges. Okay, by direct comparison test there. Okay. Okay. This next, and again, I'm sorry. I know that it gets kind of dry when I'm holding your hand through all the examples here and stuff like that. But I feel like it was kind of necessary for the direct comparison stuff. When we get to these next few here, I'll let go of my hand here a little bit. Okay. All right. Questions on any of that? Ready to move on here then? So flip over the page then. We're going to look now at a second test, okay? So sometimes we can see that a series resembles a p-series or a geometric series, okay? But we can't establish the necessary comparison that satisfies the conditions of the direct comparison test, right? So sometimes we can see, man, this is pretty close to a p-series or this is pretty close to a geometric series, but we just couldn't get the comparison to work, right? That was like example B here, right? Man, like that was close to this p-series, but it didn't quite work out because this diverged, but it also happened that this was always greater than this, and so this larger thing diverging doesn't really help us tell us anything about that. Okay, but enter in a different test, okay? When this happens, you may be able to apply the second comparison test known as the limit comparison test, okay? So, suppose that a sub n is greater than 0, b sub n is greater than 0, okay? So they're positive, right? Our sequences are positive there. And the limit as n approaches infinity of a sub n over b sub n equals L, where L is finite and positive, okay? So this is important here, all right? This value, so when you take your sequences that you're comparing, when you divide them and then take the limit as n approaches infinity, you should get, if you get a finite and positive L here, so you must get a finite and positive L. If that happens, then the two series will either both converge or both diverge. Okay? Either will both converge or both will diverge. Okay? So if your limit as n approaches infinity of the ratio of your terms here is some finite number, then that means the two series will either both converge or both diverge. All right? So this will help us a little bit here. Because when we approach infinity, we're only really worried about those like lead terms, right? Those lead coefficients and stuff like that. Okay, so what would be something, or what kind of series could we maybe compare this to? It's going to be a p-series, exactly right. And we're going to compare it. Okay, because again, where do you see the p-series here? Remember, p-series, it's when we see our n to a power, right? N to a power. Okay, if it was geometric, you'd see n in the exponent. Okay, you'd see an n in the exponent. But here we're doing a p-series because it's n is the base of the exponent. So it's n to a power. So we're going to compare to, and you ready for this? This is not going to blow your mind maybe, but we're just going to compare it to 1 over n squared. Okay. Now, if we try to do a direct comparison here, okay, if we try to do direct comparison, by the way, what do we know about 1 over n squared? It is going to what? Converge, right? Okay. So if we're trying to do a direct comparison here, we would need to show that 1 over n squared is related to the original how? If 1 over n squared converges, we want to show, and we want to show that this then converges, we need to show that this is going to be less than this, or that this is greater, right, than that, right? Our comparison there is always greater than. So in other words, we need to show this. Okay, we would need to show that. Okay, but you can kind of like cross multiplying here, and we'd have like 2n squared, which is less than or equal to 3n squared minus 4n plus 5, and it's like, okay, well, I mean, we got an 2n squared here, and then we got 3n squared, but then that 3n squared is subtracting 4n, and we're going to add 5, so it's like, you know, dot, 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 it gets messy. This one gets a little bit more messy. It's harder to compare because we took something that was more complex and made it so simple. Okay, but let's try this limit comparison idea. So again, we came up with 2 positive sequences, right? This sequence will be positive, this sequence will be positive, okay? And so then we're going to compare the sequences by dividing them. Okay, so limit comparison. And I'll zoom in some more here now. And so we're going to divide the 2 sequences. And it doesn't really matter which one you put on top, which one you put on the bottom, so I'm just going to do the original one on top and then the other one on the bottom. So we're going to have limit of 2 over 3n squared minus 4n plus 5 all over 1 over n squared. Okay, so that's kind of yucky, right? We have fraction within a fraction, but instead of dividing by 1 over n squared, what can we do instead? Multiply by the reciprocal, exactly right, okay? So if we do that, we're going to end up with 2n squared over 3n squared minus 4n plus 5. Okay, right, so if we plug in infinity here, we're going to get infinity over infinity, and we can apply L'Hopital a few times here. I'm running out of space, so I'm not going to do it. If this was a free response question, you would need to show, I would ask, please, that you show those steps for applying L'Hopital and stuff like that. Okay, so actually show that here. I'm going to, do it over and over again kind of thing, and we know it goes to what? So it's going to go to 2/3, okay? I just don't have the space here for it. But please, on a test, okay, in something that's going to be, more official, on the AP test, for example, right? Make sure you show those apply L'Hopital steps, okay? You have to do it, well, I guess twice, really, right? So... Anyway, we're going to end up with 2/3. Is 2/3, is our L here, is it finite?
Yes.
Yes. Is it positive?
Yes.
Yes. So that means, what do we know about our series here? It must converge, right? If this converges, then this converges. Okay? So, what this 2/3 means, okay, so if I just pause here real quick, all right, so again, I'll write the conclusion here, and then I'll go back to that. So since the sum from n equals 1 to infinity of 1 over n squared converges, then the sum from n equals 1 to infinity of 2 over 3n squared minus 4n plus 5 converges by that limit comparison test. Okay. This 2/3 here has meaning behind it. Okay, it's not just some random number that's well, it's not infinite, it's not negative, so it must be it works kind of thing. Right there with the gate 1 second. Okay, what this 2/3 means, right? Well, think about what we did here. We took our original series, okay, the sequence, I guess I'll say. We took the sequence here for our original sequence. We divided it, put it in a ratio with our comparison sequence, okay, and we came up with this number 2/3. Okay. So in other words, this is saying, and I'm going to run into my other problem here, but I want to write this because I think it's necessary, useful. Okay, this is saying that the sum of that series, right, 2 over 3n squared minus 4n plus 5, okay, This 2/3 is saying the series is about 2/3 of the sum of 1 over n squared. Okay, approximately. Okay, it's not exact, but it's approximately, right? Okay, because of the series there. Okay, so in other words, if you're taking something that converges and you're doing 2/3 of it, what do you know about this thing? It's going to be convergent as well, right? If you take 2/3 of something that diverges, 2/3 of something that diverges will also diverge as well. 2/3 of infinity, it will still be infinity, right? Or 2/3 of a finite number is still going to be a finite number, right? So this converging and getting a ratio there of 2 to 3 means, well, this also have to converge, okay? So that's why it's important that our L is both finite and positive. Finite and positive means that these two series really only differ by about a product of 2/3 there, okay? And that's it, or a ratio of 2/3. So this series behavior will mimic this series behavior, or vice versa, I should say. Okay. Whew, that was fun. We're good. Yes, sorry, Gabe, you had a question.
Does the sequence we're comparing it to also have to follow the, like, has to be decreasing positive or?
So good question, right? All we have to show here, all we need for this is just that they're both positive. That's it. We don't have to show the decreasing part. We don't have to show the continuous part either. Okay, just that they're both positive. Okay. So let's keep going here though. Letter B. Okay. What kind of series do we want to compare this to? Geometric now, right? Okay. What geometric series do we want to compare it to? 3/5 to the n. Exactly right. So we're going to compare verses here, that 3 over 5 to the n. Now, what do we know about 3/5 to the n? This converges. Okay. I'm going to write more in short, a little bit more shorthand here. Permit me here if you don't mind, just because of the time and stuff like that. Okay. So let's do our limit comparison test. I'm not even going to bother trying to do a direct substitution. Okay, I'm not going to bother trying to do that. Let's just do a limit comparison here. So I'm going to take this. I'm going to divide by this, which means I'm going to instead of dividing, I'll do the multiplying by the reciprocal. Okay. So again, instead of dividing, I'm multiplying by the reciprocal there. Same idea though. Okay. What can we simplify here? The 3 to the n's, right, they'll actually cancel because of simplification. So we'll have the limit as n approaches infinity of 5 to the n over 5 to the n minus 2. Okay. What will this limit be? Indeterminate. We get infinity over infinity, so we're going to apply L'Hopital's. I know, it's very exciting. So the limit as n approaches infinity, I'm actually going to do this one because it's not that bad. The derivative of 5 to the n is 5 to the n, natural log 5. The derivative of 5 to the n in the bottom, 5 to the n, natural log 5. The derivative of 2, 0, so it goes away. So we end up with this after we apply L'Hopital's, which, what happens now? Everything cancels and it equals what? Equals 1. Equals 1. Is 1 finite? Is 1 positive? So then what do we know about our series here? Converges. Okay. Question, Mike.
Does that mean, because it was a ratio, does that mean that they both have the same convergence?
So yeah, I think I'm hesitant to say like this will converge to the exact same thing as this. I'm hesitant to say that, but I think it's like the ratio, I guess, gives you kind of like an idea, because what we're comparing here are the sequences. So like the terms. So like the nth term of this, like the 100th term of this, and the 100th term of this, they will have a ratio of 1 to 1. So I guess I see what you're saying. So will they be the same thing? I mean, I guess eventually they're going to be very close to each other. But then you're adding them up. And well, but then if you're adding up to something that's got the ratio of 1. But that's the ratio is 1 as n approaches infinity. So the ratio won't be the same at the start, right? But then as you approach infinity, it's going to get closer and closer to 1. So I think the sum will still be slightly off, but the ratio is going to be, again, as you go to infinity, it's going to be close enough to 1. We can say, okay, it's just 1, and then therefore if this converges, kind of thing. See, I'm hesitant to say it's going to be the exact same thing. All right, let's look at letter C. All right, what kind of series test do we want to use here? Yes, it is a P series. Believe it or not, this is a mess of a P series, but it is a P series, okay? So, what do we want to compare? Let's just do the numerator here. What do we want our numerator to be? K to the 4/3, exactly right. Forget about the coefficients. We just want to worry about the powers, because really, when it comes to those limits, it's n approaches infinity. It's the powers that really affect things, not so much the coefficients. Over, what do we want our denominator's power to be? Very good, k squared, right? Because it's k, and that's going to be squared there. And so I can further simplify this then to be the sum of, since this is going to be a P series, we need to move things into the denominator, right? And so then I'll just take that k to the 4/3 down here as a negative 4/3. So we'll end up with 1 over 2/3, k to the 2/3, like so. Okay, what do we know about k to the 2/3? It diverges. Question? No? Okay, sorry. I thought you had a question. Yeah, diverges, okay? Diverges because it is less than 1. That's what you said there, Sean. Yeah, less than 1. That's an equal to 1. All right, so now again, let's compare these things. And so we'll, let's see here, take our, and if you'll permit me here, I'm going to do a little bit of, oops, I guess, yeah, okay, the 4/3 like that, we'll do it, okay. Okay, so take the limit as n approaches infinity, and I'm going to bring that k out of the cube root there and just make it k to the 4/3, and then over, and then similarly here, I'm going to take that 7k plus 1 quantity squared. I'll go ahead and like multiply it out, I guess, make it 49k squared plus 14k plus 1, just kind of expand it out. And again, I'll multiply by the reciprocal here, which is going to be k to the 2/3 here over 1. Okay, k to the 2/3 over 1 like that. And so then this will equal the limit as n approaches infinity to cube root of 5 k to the, well, we're multiplying k to the 4/3 times k to the 2/3. We add our exponents, so it's 6/3 there, which is really just 2. 49k squared plus 14k plus 1. And again, well, I'll pause there. So just, are we so far so good here? Sorry, I should pause. I know I'm kind of going fast here. Questions so far? So we have something times k to the second over something k to the second plus 14k plus 1. And again, we'll get, bless you, we'll get infinity over infinity. You can apply L'Hopital's here. I'm not going to do it the 2 times necessary just because it's a lot. Okay, but what do we know this is going to approach? 2 cube root of 5 over 49. Cube root of 45. Cube root of 5 over 49, which is finite and positive, right? And so since this diverges, that also will diverge by the limit comparison test. Okay. So he takes something that's very complex, rewrite it very simply, use our ratios and our limit as n approaches infinity, taking advantage of that property and stuff like that. Okay? Letter D, why don't you guys go ahead and try that one? Okay? Well, let me just get you help. Let me get you started here. What should we compare this to? What should be the numerator? N to the 8th. We only need to worry about the largest power. What should be the denominator? N to the 9th. It's n cubed, but then it's going to be 2n is going to get cubed as well, so that's another n cubed, and then it's 3n cubed. So it's n cubed, n cubed, n cubed, that's n to the 9th. Or in other words, this is the sum of just 1 over n. Okay? What do we know about 1 over n to the 1? Diverges. All right, I guess I'll just finish this off because we're almost done with it anyway. Okay? This is the harmonic series, if you remember that. We called this the harmonic series when it was a p series where p was equal to 1. Okay? What the Greeks used to help, make their harmonic notes and stuff like that. Okay? So if you'll permit me again, I'll do this one even more abbreviated here.
I'll permit it.
Thanks, Mike. I hope I don't make anyone too crazy here with that. So we'll have 8 times 3, so 24 n to the 9th. So we'll have 6 n to the 8 plus some stuff, and they'll have 24 n to the 9th plus some stuff. Right, and they're going to multiply by the reciprocal n over 1 there, which will result in 6n to the 9th as our lead term there, and 24n to the 9th as our lead term in the denominator. And so we expect this as the limit as n approaches infinity. Again, I'm skipping the apply L'Hopital stuff, all that, okay? But what do we end up with? 1 over, 6/24 there. So it'll be 1 over 4 is what that's going to equal. Okay? 6 over 24. Question? We're good? Okay, so this is finite, and it is positive, so therefore this thing will also diverge by the limit comparison test. Okay? All right. That one was pretty intense, but there it is, okay? So, objectively, you want to use the limit comparison test, okay? Use that first, all right? Don't try and come up with your own direct comparison thing and then show that one's greater than or one's less than. Use limit comparison, okay? Try to use that first, okay? Of course, you want to apply it to p-series and geometric series. Those are the ones we kind of tend to use, all right? So if you see a p-series, geometric series, apply it to that, all right? On the back of the notes here are some practice problems, okay? I would really recommend you take a look at these tonight in addition to your homework or in lieu of your homework if you only have a certain amount of time, okay? If you have to make a sacrifice or whatever, do these. Make sure you do these. When you come back tomorrow, we'll go over those first thing, okay? And we'll do that as part of the notes and stuff like that, okay? So try all, and you can use any of the series. So the homework is also, there's also homework to go, and I'll post on Google Classroom with the book and stuff like that too. But again, if you have to, do triage or whatever, please do this
What should I do
first.
with this?
So you will take that to the AP office. Do you know what that is?
Yeah.
That's part of the AP office. Okay.
Not
So yeah, if you want to go do that right now, Mike.
bad. Right this second?
I mean, if you want, if you'd like to, if you like to pack up and stuff and then go, or if you want to wait, that's fine too. There you go. Yeah, you guys can both go. Okay.
McDonald's. Oh.